Hey, my name is Tanveer. I work for IBM, and today we are going to see how to build a multi-node GPU cluster for the distributed deep learning. And I'm going to do it on AWS. The reason for selecting an AWS is because like my machines or my the environments is on the AWS itself. The stuff that we are going to see in this tutorial are like in general applies to all the other cloud platforms or on the custom or on the custom GPU machines. If you have something on-prem, there are certain things which are specific to AWS. Amazon has built its own specialized tech stack on top of what's available from NVIDIA uh, for enabling the distributed deep learning and the distributed machine learning workloads. So those tech like enhance what has been offered from the NVIDIA, okay, to another level. So there are like some optimizations which AWS has done in-house. So we would need to like install or we would need to like set up those components as well. So those will be like specific to AWS, but in general, like other stuffs will be common wherever you want to build this cluster. So in this session, we are gonna see like few things like that, how my environment looks like. I'm gonna give you a brief walkthrough about my environment. Why do we need to do a distributed deep learning? Okay, that's another thing which we are gonna look at shortly. And I would need to show you like how to build that setup for distributed deep learning, which includes like the multiple machines, the multiple GPUs, and how you can trigger your workflows over there. I'm gonna explain like each component briefly, which we are gonna set up. So those introductions, those that explanation is on a very brief and on an introductory level, just to make you aware of like what we are trying to do. And in the last, we'll just set this, we'll just test this entire setup. So the setup that I have is like two P4D 24x large machines on the AWS. One machine has like eight 800 GPUs with 40 gigs of GPU memory. So in short, like my one machine has like 320 GB of GPU memory. So total, I have like two machines. That means like I have like 16 GPUs, which are like 800, and total I have like 640 GB of total memory. So it will briefly look like this. Like this is GPU one to GPU 8. This is my machine 1, and this is my machine 2 with GPU 1, GPU 2 to GPU 8. So in this tutorial, like how to build a setup, okay, in which we can use both of these machines, okay, together to fire a distributed deep learning workflow, which could be like training a large language model, or training a large vision model, or like training on a very huge amount of the data. So I'm going to show you on the AWS as well, like what I have it, okay, and why do I need to select those things. So here we are on AWS. Okay, where my AWS has gone. OB is showing, yeah, OB is showing properly. Okay, so I have this two P4D 24x large machines. Okay, and if you go to AWS website, there is a good tutorial about getting started with EFN and CCL. Okay, this is the tutorial which tells you like how to set up your distributed deep learning and distributed machine learning workloads. They should have like modified their heading to include the distributed deep learning and the machine learning workloads on EC2. The thing is like the tech stack which is required to enable the distributed deep learning or the distributed machine learning needs like some specific technology. Okay, which the primary technology that it needs is NVIDIA uh, Collective Communication Library, which is NCCL. okay, and which basically enables the communication between the different GPUs on the same machine and the different GPUs between the different machines, and it takes care of all the management and the housekeeping over there. And EFA is something called as elastic fabric adapter, which which is something which was developed by Amazon, which works in conjunction with NCCL with some optimization on top of it. So not all the instances on the AWS are like supports this stuff. There are only four types of instances on the AWS which supports this thing. So one of the instances like P3DN 24x large, P4DN, P4D 24x large, P5 48x large. I'm sorry, like there are three instances, not the four. And those instances, you just need to like have one of these three instances to do the distributed machine learning on the Amazon. You can have one machine like which is like some G version or so, which could have like the multi GPU. So you can use the one machine with the multi GPU setup, but you cannot use a combination of machines with the multiple GPUs and without like other than these four instances. One of the important things that you would need to consider, there are two important things that you would need to consider while spinning up this machine. Okay, when you launch the machine, okay, you have to update your inbounds rules and outbounds rules. And there is one more thing that I'm gonna tell you like quickly, shortly, not quickly. So in the inbound rules, you have to allow all the traffics, okay, from the security group that you had created, and from the outbound rule, okay, you would have to do the same thing. The thing that you would need to specifically take care, okay, while launching those instances, is you need a network interface card which is EFA enabled. Okay, so you can select the instance. Okay, you need to go to the networking, which is here. And on the networking tab, you'll see like there are some network interfaces. Okay, so you have to select the network interface and you need to check for this setting. This is Elastic Fabric Adapter, which was developed by Amazon. It's a proprietary Amazon technology and it has to be true. If the EFA is not true, even though you have this one of these three instances, P4D, even if like you have this one of these uh, three instances, this P3DN, P4D, P5X, and if they are not enabled with the elastic fiber adapter, okay, that's not gonna work. So while launching the machines, okay, or like you can modify the adapter even after the launch of the machine. So like before starting with the setup, make sure that you have these settings enabled and you have your like rules updated to like the inbound and outbound rules updated to this manner. I'm going to post this link as a part of the description so you can take a look at it. Now let's go back to the setup. Okay, I had this machines. I did an SSH on this machine using the PEM files. So I am on this machine. Okay, so I'm here and let's start with the setup. So the tech that we are gonna use, just 1 minute, I don't know what happened. Command I, okay. So the tech that we are gonna like install or like the components that we are gonna set up in this environment, okay, I'm gonna just list it down the components and which are the I'll just do a classification like which are the generic component and which are the AWS specific components. So the tech component that we are gonna set up are NVIDIA or I can give you a hack as well to avoid like some of the setups. So it's NVIDIA CUDA toolkit. It's like something which is generic. Okay, then you would need the NVIDIA GPU driver. The third thing that you would need is CUDNN, which is CUDA Deep Neural Net Library. The fourth thing that you need is something called as a GDR copy. This is a very interesting component, okay, and this is again a general component, this is again a general component, this is again a general component. The fifth thing you need is EFA, which is Elastic Fabric Adapter, okay, which is a software, okay, from AWS. So this is something which is specific to AWS. Then you need our favorite NCCL, NVIDIA Collective Communication Library, which is again a generic. Okay, then you need something from an AWS, which is AWS official NCCL plugin. So this plugin basically works with the NCCL onto their AWS specific environment. This is a network interface, okay, which basically works with an NCCL to do like some job on top of the NCCL. And then we are gonna test it out. Okay, one more thing that we would need is NVIDIA Fabrics. Okay, NVIDIA Fabrics. Just to write it is NVIDIA Fabric. Okay, so there are like two ways to do it. If you go the tutorial on AWS, okay, they'll ask you to like spin up a temporary instance, okay, do all this setup on a temp instance, and then build an AMI image, and then go back and launch your the instance, okay, your permanent instances on which you are gonna do this job, okay, using that custom AMI image that you built. But one of the problem that we have seen with an AWS is like the availability of the machines like A100 is very limited. So like a lot of times you don't get it. Okay. So the way that we did was like we launched the two machines. Okay. And after launching those two machines, okay, we launched it first, and we launched it in a manner that we had that EFA enabled, and we put those inbound and outbound rules as recommended by the AWS, and we launched it with the deep learning AMI image. So if you launch a machine with the deep learning AMI image, you get a lot of things pre-installed. So the things like this NVIDIA toolkit, NVIDIA GPU driver, okay, CUDNN and GDR, the NVIDIA Fabric Manager, and the GDR copy will be already installed on the deep learning image. So in our setup on these two machines, we spun up with the deep learning image, okay, and we had all those things installed for there. If you don't have it installed, you would have to follow the instructions to like install all those four things, which I'm gonna skip here, but I'm gonna show you like how to test these things. How to like test the above components on your EC2 or on your machine, and briefly explained each of them. Okay, so let's start with the first thing is the NVIDIA CUDA toolkit. So NVIDIA, like the CUDA is something which is giving an edge to the NVIDIA with respect to the other manufacturers like AMD and the Intel. And the CUDA is like one of the reason, like apart from the GPUs, it's a software framework which NVIDIA has built, and which is making like NVIDIA more successful. Okay, so the CUDA toolkit is like a comprehensive software development platform provided by NVIDIA, and this basically enables the developer to utilize the NVIDIA GPU for parallel computing tasks. Okay, it offers a range of tools and libraries and like some compilers, okay, that makes it easier to develop, optimize, deploy the GPU accelerated pipelines. So the CUDA toolkit has like few of the components, okay, and I'm gonna list down those components. The first component is the CUDA compiler. Okay, so CUDA compiler is basically a compiler which combines the CUDA code written in like mix of C, C++, and some CUDA extensions into a form, okay, that into a form that the GPU likes, or into a form which can be executed on the GPU. The another components inside the CUDA toolkit is the CUDA libraries. Okay, so to CUDA libraries are the different libraries which you would need to put it on, which you would need it like to make your deep learning workflow works. And one of the famous library is CUDA BLAS, okay, which is like the CUDA enabled or the GPU. Oh, sorry, my G is bad. GPU accelerated basic linear algebra. So we all know like the linear algebra, right, is the heart of the deep learning, right? Most of the deep learning operations goes back to the roots of uh, uh, the linear algebra or the fundamentals of the linear algebra. So the CUDA BLAS is a library which basically has the implementation of this basic linear algebra operations, okay, which can be accelerated on the GPU. So they built their custom implementations of the linear algebra operations, and which can run much faster on the GPU. So the CUDA plus that. Another important component is CUDA FFT, which is the CUDA enabled fast Fourier transform. So in like the task like computer vision, right? FFT is something which is very fundamental to any of the operations which you want to do in the computer vision. And the CUDA CUFFT has the like the GPU accelerated implementation of FFT. Then we have CUDA random number generator. Again, the random numbers are very important entity in any of the deep learning framework, right? You would need to deal with a bunch of random numbers, right? When you initialize a neural network, like it starts with some random numbers, right? So the CUDA rand generates the random number generation using GPU. The other thing is CUDA parse or CUDA sparse. Okay, not CUDA parse, CUDA sparse. So the CUDA sparse is a library which basically does the GPU accelerated sparse matrix multiplication, right? So we know like a lot of times this this uh, this matrices are like the sparse, and like multiplying the two sparse matrices needs a lot of an optimization to get that done in a faster manner. So it basically get this sparse matrix multiplication onto the GPU. The another is like thrust. Okay, so the thrust is a C++ template library for CUDA. Okay, using the standard template using STL. Okay, then what we have it is the CUDA runtime and the CUDA drivers. CUDA runtime and driver API. So basically, CUDA runtime provides a high-level programming interface for CUDA, while the driver API provides the more fine-grained controls to the advanced users. So the people come and can create their own CUDA kernels, which interacts with the CUDA, and this driver API gives them more handle on a system level. and these are the entities which allows the developers to manage the memory, the GPU memory, launch their own kernels, like handle the GPU operation. So it's a pretty system level, okay, which most of the app users don't use it. Okay, then there are some debugging tools and profilers as well as a part of the toolkits. So one of the the profiler is CUDA GDB, which is like CUDA-ware version of the GDB debugger, which is an OpenGL debugger. So I'm going to show you like how to test for at least these things, okay, if they are pre-installed on the machine. And as I said, like I installed the machine using a deep learning based image, okay. So I'm hoping like this CUDA toolkit, okay, will be installed over there. Oh, one more thing that I missed is the CUDA NN, okay. I'm sorry, I apologize for it. So CUDA NN, which is CUDNN, which is the CUDA enabled this deep neural network library. So it's GPU CUDA enabled GPU accelerated deep neural nets. Okay, so these are designed for like have creating your own deep neural networks and enabling the deep neural network applications. It basically optimizes the performance of the DL frameworks on a GPU. So you've seen like the famous like PyTorch or Torch, okay, or TensorFlow has two options. One is like your CPU based version, another is a CUDA based version. So whenever it has the CUDA based version and when they had the CUDA DNN enabled to it, okay, your frameworks are gonna interact with the CUDA NN. So the basic benefit it offers is like optimized primitives. So they have an highly optimized implementations. Okay, of standard deep learning operations. So what I meant is like the PyTorch has its own. Let's say PyTorch has its own implementation of like the convolutional neural network, right? And when you don't have a GPU and when you run it on a CPU, it's gonna use the PyTorch version of the convolution. Okay, but when your system detects like you have the CUDA, when you have like CUDNN or the CUDA deep neural network libraries, okay, and when you have it is enabled and when the system detects it, then instead of using the native PyTorch implementation, it goes and it uses the highly optimized implementation of the convolution or an activation function from this framework. Okay, so now let's switch to the machine. Okay, and let me show you how to figure out whether they are installed on it or not. Okay, so let me close this thing. So I had like written some of the commands, okay, for doing this task, and I'm gonna walk you through that. So NVIDIA SMI is like the favorite commands for working with the GPUs. Okay, so you can see like there is an NVIDIA driver available, which is of version 535183. Okay, so we have this installed. Okay, we can see the CUDA is also there. The CUDA is with a version 12.2. Okay, and the number of GPUs we have on this machine is the eight GPUs. So we can like mark our checklist about the CUDA NN, sorry, not CUDA NN, the CUDA toolkit, the NVIDIA driver. and I'm gonna check it on the compiler as well. So we can see this NVIDIA CUDA compiler is also there. Okay, so let me go back to my notes, okay, and see. Let me take it like green. So we tested is check. This is check. This is check. Okay, so we check the compiler, we check the GPU driver, and we check the toolkit. So these are the three things that we checked. Now let's move on to, yeah, NVIDIA Fabric. So that's something that I didn't check it earlier. Okay, so we are gonna figure out whether we have the NVIDIA Fabric Manager or not. So I'll go to this thing. Okay, let me figure out here. Let me go here. Okay, so I'll just try to enable it, this NVIDIA Fabric Manager, and see if it's exists or not. Okay, so I'm gonna go here. Okay, I'll just clear the screen. Oh, it worked. So that means like I do have this NVIDIA Fabric Manager installed. Okay, and I'm gonna talk briefly about the NVIDIA Fabric Manager as well. So let me switch back to my notes. Okay. So the NVIDIA Fabric Manager. So we have been seeing the setup that I had it. Oh, I'm sorry. Is okay. Like this machine. Oh, why I'm writing with blue. So I have this machine. Okay, with 8 GPUs. Okay, one, two, three, four, five, six, seven, and eight. This was my machine one, and I have like similar other machine, right? So since we have this different GPUs, okay, so a lot of data is going to transfer between these GPUs, right? Between the machines, within the machines. So let me just mark the data transfer with a different color. So I'll use this red color with the data for the data transfer. So the data is gonna move from here, the data is gonna move from here, the data is gonna move from here, the data is gonna move from here to here. So all sort of like the data transfer could happen, right? Data transfer. So so a lot of communication is gonna happen between these machines, okay? And to enable the faster communication between the GPUs, this could be like within the machine or like between the machines. So NVIDIA come up with like two things. One is like NVLink and another is NVLink switch. So these are like a custom piece of an hardware. Okay, this machines comes up with this particular thing. Okay, and they are the kind of a building blocks. Okay, building blocks of high speed multi GPU communication, of high speed multi GPU communication. Okay, So they basically helps in like feeding the large data sets into the model. Okay, so you could have like the data set over here. So the data set needs to go there. Okay, and all of those things, right? It happens over there. So to serve a billion parameter model or to train a model, like you would need an efficient communications between the GPUs. And this is what the NVLink does, right? High speed or uh, efficient communication between GPUs. Okay, so what this Fabric Manager is, right? So Fabric Manager is a service actually. Okay, it's a software stack from NVIDIA. Okay, to manage and optimize the use of NVLink. Okay, the use of NVLink and NV switch. Okay, and it interconnects between like the GPUs and like multi GPU system, and this helps in like the better communication, right? So to build a multi GPU system, what we basically need, right? We need a better communication because in deep learning, we'll have very large amount of data. We'll have very large amount of parameters. These two things can't fit in one GPU or in one machine, right? So we would have to like that's the reason like we are doing the distributed deep learning, and any of the distributed framework needs a faster and effective communication. So that's the job of like this unveiling does. Okay, now we are gonna look at something called as GDR copy. Okay, that's interesting thing. The G oh I'm sorry, the GDR copy. Okay, so it's an interesting concept. Okay, in like this multi GPU communication. So basically, GDR copy is GDRMA. Okay, which basically stands for GPU. Oh, my U sucks as well. GPU direct remote directory directory management access. Okay, so what basically this direct memory direct remote the direct remote directory management access stands for. Okay, GDRMA. So GDR is basically a technology that enables the direct transfer of the bit. So it enables the direct transfer of data between the GPUs. Okay, so traditionally what happens, like what do I mean by like the direct transfer, right? So here I was showing a picture, okay, in which like the data is being transferred between one GPU and another GPU. And our friend GDR copy basically enables that. If the GDR copy is not there, okay, so traditionally without GDR copy, the data transfer between the GPU would look like would look like uh, would look like this. Okay, so would look like the GPU is there. Okay, there is another GPU 2. This is GPU 1. This is GPU 2. Okay, so and then there is this main memory and then the CPU. So to like we cannot without the GDR copy we cannot do this thing. So this wasn't possible. Okay, so the data has to copy it from the GPU one to the main memory, which is basically a RAM. Okay, and the CPU has to copy the data from here. So the first step is to like get the data from GPU one to the main memory. The CPU get involved. The CPU has to take this copy of the data and have to put it to the GPU two. Okay, as a part of the data transfer. So the direct communication was not there. Okay, and this is a tech which basically enables the direct transfer of the memory between the GPUs. So with the GDR copy, okay, we can do this to this, or this to this, or this to anywhere. Okay, without involving without involving the CPUs and the RAMs. So the direct communication is like beneficial in many ways. Okay, uh, the direct communication is like optimized, it's faster because you are not going to an additional hop, right? You are not moving from GPU to the main memory, okay, and from main memory it's going back to the GPU. So there are like what one and two copy operations, which has been like reduced to just single copy operation between the GPU itself, okay, and it minimizes the latency. Okay, and it maximizes the bandwidth. So one of the one of the reason that one of the design principle on the GPUs were built is they were optimized for the latencies, right? So they were optimized for they were optimized for like transferring the large amount of the data. Okay, so this GDR copy exploits that fact as well. Okay, so now we need to like check the GDR copy as well. If we have the GDR copy, if we have the GDR copy on our machine or not. Okay, so I'm gonna just add, oh, before that, I'm gonna set this path, okay, for the things that we installed. Why I need an inspector? I don't need an inspector. So I'm gonna clear the message. I'm gonna do an add to the path to the CUDA, okay, and then add this, the CUDA PT and other stuff. So now, yeah, we are going to see about the GDR copy. We have the GDR copy as a part of the deep learning image. So when we fire this command, okay, it's going to take some time and it's going to do some sort of a sanity. So it's going to fire, I think, like 28 or so tests, okay, to basically see whether we have this thing. Okay, so it's running the GDR copy. So this concept of like direct communication, like the direct data transfer between the GPUs, right? NVIDIA built it like they optimize the GPU the communication between the GPUs, okay, and without excluding the CPU. So your CPU like stays free, right? You don't have the multiple copies of the same data at the multiple places, right? So when you are using the CPU and the main memory as half, the data goes and sits over there as well. So that part is something which has been eliminated, okay, on this thing. It's taking some time. Okay, let's take the GDR copy is an amazing is a good addition. Okay, so it's still running. We have to wait for some time to complete. Okay, we have what? How long? I don't know. GDR copy sanity. I should have like run it once. Okay, it would have been faster. So, like, yeah, by the time the GDR copy gets complete, the test gets complete, we are gonna look at the other component, which is basically, let me switch back to my notes or my presentation screen. Okay, we have it here. So we are gonna look at the AWS component, which is EFA, Elastic Fabric Adapter. Okay, so we have seen like what does this okay, that GDR copy is complete. So I'll go back there and we'll finish that part of. Come on, man. So where is my, yeah. So we can see like the GDR sanity worked. Okay, it passed like all the 28 tests that it has, and it shows like we have the GDR copy installed. If you want, we can run another test like GDR copy VW. I'll just pair it. Okay, it's gonna take some time to do. Okay, yeah. So we can see like the GDR copy is also there. So I'll go back to, I'll stay here. I'll go back to my notes. Okay, and we'll do a tick mark on the NVIDIA Fabric was there. So we had it checked. Okay, well, what color I was using? This one, right? We have it checked. Okay, and we have the GDR copy checked. Okay, so that part is done. So now we are left with like three more components: EFA, NCCL, and AWS. The EFA is AWS specific thing, and we are gonna look at what the EFA is. Okay, so EFA stands for, like as I said, Elastic Fabric Adapter. Sorry for like diversion to go and verify the GDR copy. So EFA stands for like Elastic Fabric Adapter on AWS instance. This is a network interface. So EFA is nothing but a network interface, right? So at the start of the video, I have requested you to check like whatever P4 or like whatever those three instances that you had used had this EFA enabled or not. It's a must requirement, okay, for this setup that you need to have an EFA on it, okay. And what this basically does is specifically enhance the performance of the high performance computing, which is HPC, and the distributed deep learning workload. It enhance the performance. See, there is a lot of communication happening between the GPUs, right? One GPU is here, another GPU is here. There is a communication happening, and there are like and this interface card. Sorry, one machine, and this is another machine. Okay, with bunch of GPUs here, bunch of GPUs here. So there is a network interface card, right, which basically let it do it. So that the network interface has to be the EFA enabled. Okay, and it improves the performance that requires, again, it goes back to what? The communication, right, between the machines. So the GDR copy was like related to what, like the communication between the GPUs, okay, and this EFA is basically helps to communication between the machines or the nodes, okay, or the compute nodes. So again, the feature of the EFA is like low latency, okay, higher bandwidth, and in Amazon, okay, it's the only EFA, okay, only EFA enabled adapters, EFA enabled interfaces supports GDR copy. So if we want to do a direct data transfer between the machines, or between the GPU, sorry, I'm sorry, between the GPU, which GDR copy does on AWS, we need to have EFA enabled and installed. Okay. So I hope like we made a good case for like EFA and the direct data transfers. So I'm gonna now we are gonna see we need to install the EFA, right? So EFA doesn't comes out of box with the AWS. So we are gonna see how to install it. Okay. So I'll just go to the home directory here. Why this is not there? Okay, so we are gonna see like how to install this guy, our friend EFA. So I'm gonna go back to my this thing. The first thing is like we are gonna do a curl to get the tar.gz. So yeah, so I got this thing. It was pretty quick. Now I'm gonna untar the tar.gz file and would have to get into this EF installer, the untar folder, so that we can run the EFA installer. Okay, so I'm gonna untar it, the ampersand n will concatenate this thing, the cd command. We'll check the directory. We are into the directory. Excuse me. Now we are gonna run the sudo to install the EFA. So now EFA is gonna get installed. Okay, you'll get a bunch of messages. So in this entire this distributed deep learning framework, right? The data communication or the communication between the different machines data is the most critical thing, right? And you can see there is a lot of tech around it. Okay, so it's testing it out. It's starting a server. It's starting a client. Okay, it got installed. So a lot of tech is there to optimize the data transfer, right? We have seen there is something called as a GTR copy. There is something called as an EFR. We are gonna see NCCL, right? All of those things are like just to optimize or make the efficient data transfer between the GPUs, between the machines. And this is where like most of the latency or most of the like the time would lie, right? The GPUs are powerful enough, so they do have like a lot of cores with them to process. But the point of struggle with the GPUs right now is to get the data to the cores to process it, right? So the data latencies are still the critical points, and that's the reason we are seeing uh, a lot of tech around it, just improving it out. And they've invested a lot. So it's running. Okay, by the time it completes, I think it's gonna fail or so. So we are gonna just fire this thing. Okay, I don't know about the ping pong test, whether the ping pong test is gonna succeed or not. Let me just cancel the ping pong text and see. Okay, I just cancel the ping pong test. We'll run the EFA. Okay, we can see that's an EFA thing. Okay, EFA 27 RDM protocol. Okay, I fired this command as well. Okay, sudo. Let me just reboot the machine. So one of the recommendation after the EFA is to just to like reboot the machine. Okay, so I'm gonna reboot the machine, and we are gonna just connect to it. Ideally, we should have seen a different outcome. Okay, yeah, we are gonna see the same thing. 24x large with the multiple network interfaces. I don't know. We have one interface or we have the multiple interface. Let me go to the other machine that I have it. Okay, which I already built it. So this is the second node that I have it. I'll fire the TFA. The same configuration. Okay, TFA is there. Okay, the operation got timed out and the machine is not rebooted yet. Oh, we are there. So I'm gonna fire it out. Okay, can we see the display? Can we see the output? Ding, ding, ding. If we get the output here, we'll have this thing up and running. Come on. Bit fast. Ah, yeah, we got it. So we got the EFA installed. Okay, let me go back to my notes. Okay, and we'll mark the EFA as checked. Up, 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 up. Okay, and we have EFA checked. Now we come to the very important component, which is NCCL. Okay, this is NVIDIA Collective Communication Library, and this kind of a backbone. Okay, for the entire thing. So let's go down and see what the NCCL is. And once we see it, I'm gonna like install the NCCL over there. So NCCL stands for NVIDIA. Wow, I spell it bad. NVIDIA Commons, NVIDIA Collective Communications Library. Okay, so this is what the NCCL stands for. You can treat it as a like backbone for all multi GPU in a machine, all multi GPU setups. Okay, all multi GPU clusters, multi GPU, multi machine clusters, I would say. So it's basically developed to optimize and accelerate the collective communication primitives. So the reason for building this, reason for having NCCL is to develop and optimize and accelerate develop or to develop. Oh, sorry, is to the reason for like developing NCCL is to optimize and accelerate collective common communication, right? Yeah, it's communication primitives, which are used in parallel, which are commonly used in parallel computing in or on multi GPU systems. So basically, what are these parallel communication, collective communication primitives, right? So there are certain operations, okay, which are common in parallel processing. And one of the common operation is called reduce. Okay, so what happen is like you have this multiple GPUs. Okay, this is GPU one, this is two, three, four, and you have this piece of data. Okay, you give some data to this GPU. Let's say this data to this GPU, this data to this GPU, and this data to this GPU. So in like from a full slice of the data, you like broke down the data into smaller pieces, okay, and you gave the GPU, and all of the GPUs are doing parallel processing, right? So what our friend like this reduce operator does is it. So once this GPU performs their computations, right, they are gonna send the results back. So I should have like drawn it better. Let me just write better. Reduce operator, okay. So you have this data slice, and you have this GPU1, GPU2, GPU3, GPU4. Okay, you give the data to the GPU. So that's that. Okay, and the each GPU is processing, right? So this is slice 1, this is slice 2, slice 3, slice 4, and all of them are processing in parallel. Okay, so once this processing is complete, they have to send the results back, right? So this GPU will send the results 1, this GPU will send the results 2, this GPU will send its own results, this GPU will send its own results. So R1, R2, R3, R4, right? And what the GPU has to do is to accumulate the results, right? So the reduce is a very common, and that's what the reduce operator does, right? It's basically combines the data from all the GPU, combines, oh sorry, the data public results from all the GPU, consolidate it, and report it back. So there are like few common operations, okay, which basically are common in all sort of like parallel computations and the multi GPU. So NCCL basically provides an implementation for common, all those collective, not common, all this collective communication operations. Okay, so other collective communication primitives, collective communication. I'm sorry, I'm messing it up with collective with the common. Like reduce. Then there is a broadcast operation in which the data is sent to all the GPU, right? The same amount of the data is sent to all the GPU. It's like a broadcast message. Okay. The other operation is called like gather. okay, which basically gathers the data from the GPU and distribute the combined data. Um, Gather is basically to collect the data from the GPUs and distribute the combined data to the GPUs. Then we have like something called the reduce scatter, okay, which is another operation. So NCCL supports both, okay, multi GPU, oh sorry, multi GPU and multi node configurations, right? And it does have the support for this GPU direct or DMA, okay, which is our GDR copy or good old friend, which enables the direct data transfer between the GPUs without involving the CPU. It helps us in like scaling, right? So it helps us to achieve the scalability. So if you have a bigger workload, right, with the help of all those things, you can add more machines. So this is machine, this is GPU, this is another machine. Okay, if your workload doesn't fit in, you go ahead and add another machine. If it doesn't fit in here, you go and add another machine. So that's how like you can achieve the scalability part. Now going back to install this NCCL. Okay, so I'm gonna switch back to my Mac. Okay, I'm here. Okay, I'm gonna do the clear. Okay, and okay, I have to stop the terminal. So where I am, okay, yeah, here. So I have to go to this directory OPT, okay, and then we would have to uh, clone this repo. Okay, so I cloned it. I'll just go and check it out there. That part is done. Okay. So we cloned it and we have gone to this folder. We have basically cloned a Git repo for NCCL, which comes from an NVIDIA, and we are into the cloned code. Okay, NCCL. Oh, sorry, I'm already there. So I'll do a pwd. We are there. Okay, and now we are gonna build it. Now we are gonna build it. Now to ship. Okay, so it's building it up. Mm. So yeah, one thing like this NCCL is generic, right? It came from an NVIDIA. So even if like you want to build your multi-node on-prem cluster, okay, you would have to have like this NCCL installed on it. So yeah, here is an operations, right, which collective communication primitives, right? This is a broadcast primitive. This is the gather primitive, right? These are the various reduce sum, reduce min max, okay, reduce sum post division. Okay, so these are the various primitives, okay, which they are installing all reduce, okay, reduce scatter. This is gonna take some time. So after that, we will be just left with like two more stages. Okay, since we installed in NCCL, right? NCCL is something common, but the AWS has its own EFA network adapter, right? So there is a another software layer which AWS has put, okay, by integrating the NCCL with the AWS infrastructure. Okay, and that's the next component that we are gonna look at it up. So I let it install it, okay, and we are gonna check to the other component for now. Okay, so I'll just do to my iPad. Okay, so we are here. So we'll go up. Yeah, we are here. So NCCL, yeah, it's a general thing. Okay, we are installing it out. I'll keep on checking in between if it's done or not, but it's still is compiling. So we look at this AWS official NCCL plugin, okay, and what it is. So we are gonna look at this AWS specific component. So we have this AWS infra, right? And there is this NCCL. So there is a software component, okay, which is called as AWS official NCCL plugin. Okay, so what it basically does is, okay, that it facilitates like the communication between the GPU across the multiple nodes. Okay, so you have this one machine, you have another machine, you have this third machine, okay, and this plugin basically acts as an interface, okay, between NCCL. So NVIDIA stuff like understands an NCCL, but AWS has its own infra, right? They have done some network level optimizations using this elastic fabric adapters like the lip fabric thing. And the lip fabric has a kind of a connectionless, reliable, connectionless protocol, which is like very reliable in the AWS environment. So this NCCL has its connection-oriented transport APIs. So this plugin, okay, maps, okay, plugin, oh, sorry, plugin maps your, what do we call, NCCL stuff to lib fabric, which basically talks to the AWS infra. Let me see. Okay. So yeah, that's what the NCCL is. We'll go back and we'll check, okay, whether we have this good friend that NCCL was installed, okay, and it seems to be compiled. Okay, so we have this NCCL compiled. That's a good news. So let's move on to our next friend, which is this AWS plugin. Okay, so we'll go to the home. Okay, once we are there at the home, okay, so we are gonna install this thing. I need to update my stuff here as well. So install, then what we are gonna do? We are gonna basically do a duplicate, okay, from this plugin. So we are gonna again do the wget for this tar.gz. Once we have the tar.gz, we would have to basically untar it. Okay. So we are gonna untar and get into the directory. Okay, so we did a wget. We are gonna untar it. Okay, this is where we are gonna untar. So we untarred, we are there in the directory. Clear the screen, and we are gonna generate the make files. Okay, so this is like generating the make files. So we generated the make file. Okay, this MPI is the message passing interface. Okay, which basically enables the communication between which is basically very essential critical component for any parallel processing framework. It has a very high throughput message passing mechanism. The fabric we have seen developed by this fabric adapter, okay, for efficient communication. NCCL is there and the CUDA is there. Now, now I'm gonna configure it, okay. So check. Okay, now we are configuring. Oh, we have configured it. Congratulations. And oh, sorry, we have just generated a make. Okay, now I'm gonna export the path for MPPI. I think it's already done, but I will do it again. And now we are gonna install it. Okay, so we are building this guy. Okay, cool. So we are done. Now what we need to do is to test this entire setup, right? So to test the setup, okay, so NCCL has testing. So we need to install this NCCL test. Okay, so we'll install it, and post that after installing, okay, we are gonna do a single node test with one GPU and with multiple GPUs. Okay, so let's go back to the Mac. Okay, so we are gonna go to again a home directory. Okay, so cd home, I am at home, pwd. I need to do a clone for the NCCL test, which NVIDIA has gracefully released for us. We are into the directory. Okay, once we are in the directory, okay, we are gonna export the things. Okay, so we have to export the EFA. So the EFA is exported. Yeah, here is my thing. Okay, and now we are gonna make it. So we are gonna install the test, right? So to install the test, okay, so again it's gonna compile. So these NCCL tests are released by this guy is NVIDIA's. Okay, so we are gonna install it and then we are gonna test it. Hmm. So to test this NCCL configurations, okay. So with an Amazon, there is an IMD instance metadata services. So there is this machine 169.254, 169.254. You can query this machine to get your instance metadata. So we are gonna take a token and then we are gonna obtain the IP address of the machine and gonna create a file called myhost, okay, to configure and to run the test. These tests are still compiling, so it's gonna take time. In the meantime, we'll look at the test. So as a part of the test, okay, we are gonna run a distributed application using MPI run, which is basically which comes from an open MPI, okay, and which basically has an MPI processes runs on 8 different MPI processes. Okay, in the first stage, we'll run on a single CPU and on a single GPU, and we'll run it on the multiple GPUs. Okay, so basically, we are gonna do this collective communication primitive of all reduce, okay, over there. And there are certain, okay, this thing, uh, this environment variables, okay, there's an environment variable for using EFA and GDR copy this remote directory management access on the EFA. Okay, then these are like path setting for CUDA, EFA, OpenMPI, or AWS NCCL plugin. Then we are going to put the debug level to info. Then this is a host file. This is gonna list down the machines, okay, where we have the nodes, okay, the IP address of the machines where we have the GPUs, which we want to test it out, or where this MPI is gonna run. Since we are gonna run it on one machine, we are gonna provide an IP address of this machine only. Otherwise, we are gonna if we have the multiple machines, we have to provide the multiple IP addresses of each machine. Okay, this specifies the total number of MPI processes to run, like how many processes want to run. Okay, and this thing, this capital N, okay, this is the number of processes, and this is like how much to run it on each node. Since we have only one node here, it means like all the 8 processes are gonna run on one node. Okay. Then these are like some MPI bind to none. This option disables the process bindings, meaning that the MPI processes are not bound to any specific cores. Okay, and these are like the reduce operations. Okay, how much data that you want to reduce and all. Okay, cool. So we have installed the test. Okay, now what we need to do? We need to go and do this step. Okay, we have to obtain the token by calling Amazon instance metadata services. Okay, I'll do 1 second. Excuse me. Okay. Um, 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 okay, so we run this thing CD and CCL test. Okay, so we are gonna get the token. We got the token. We'll look at how the my host file looks like. Okay, so we have this single machine, right? We want to test it on a single machine, and now we are gonna put that thing. Oh, sorry, I need to rm minus r my host. Okay, I think I have done it. Oh, I could just combine those two things into one stage only, so I don't need this thing. Okay, so basically we are gonna test that thing, the test setup now. We had, oh sorry, where were we? So we had, I have to explain all those things. Okay. My recording unfortunately got stopped. So where were we? Where were we? We built the test. Okay. So I had combined, like we were here. So I had combined these two stages, right? We are obtaining the token from this Amazon instance metadata services. Okay, and putting the token into a file called as my host. Okay, into one stage. So I'd removed uh, this file my host. Okay, and I'm gonna run this. So this is an IP, like where you can make a call and you can get an metadata about your instance. So and then I'll obtain a token for it, and using the token, I'm gonna extract that my IPv4 and put that into the host. So we are gonna test that NCCL and EFA whether they are enable it or not on the single node configuration. So my host will look like this. Okay, so there would you go. So I'm gonna test it out now. Okay, with this thing, and we'll put it on. I think I already explained out this stuff, right? So this is for like using an EFA. There are this various paths, okay, for using MPI, CUDA, and the stuff. This host file will contain the name of the host. So if we have the multiple nodes, okay, we are gonna put the name of all the hosts over there. Okay, say n minus 8. This small is like n8 is like the number of processes that we need to like run. How many number of MPI processes we need to run, and this bigger and specify like if we have the multiple nodes, that how many processes has to be executed on the each node. Since we just have one node, so all these 8 processes will execute on the one machine itself. Okay, these are like some so the collective communication primitive that we are going to test on any MPI is this already is pref. So we submitted a MPI based process, which is an MPI run, and we see the results, and there you go. Okay, looks like all good. I'll just clear and run it again. Okay, so it got all the GPUs, right? One, two, three, four, five, six, 7. Okay, and it's running. Rank 4, rank 5, destroy completed. Okay, and we'll run it with one rank 2. Okay, CUDA dev 2 bus ID 2 destroy completed. Okay, I'm gonna run it with an additional parameter for like CUDA visible devices so that all of those GPUs will be visible. And let me fire it over here. What results are expected here? Oh, cool. Let's run it with the debug log as well for once. Hmm. There you go. Debug. Hmm. 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 Yeah. So we got this thing. So we ran it. Okay. And here we run it, right? So to NCCL plugin, the topo file variable. Can this be called additionally? Setting F1 EFA bytes supported. Hmm. What was the statement? Selected provider. The chunk size. So I got the topology thing in. Hmm, using ENS trade setting. Official NCC selected NCCL protocol to simple using network AWS provider. Yeah, we got the lib fabric versions and selected provider filter to EFA. Yeah, we got it. So it seems like our EFA and NCCL both are working. So as a part of the last stage, what we need to do is, okay, so we have this thing, right? The machine one with CUDA, Fabric Manager, CUDA and EFA, NCCL, GDR copy, AWS plugin, NCCL test. We have to replicate the same setup on the second machine, and we have to build a passwordless connectivity between the two machines. So we need to like generate a key, okay, SSH key from this machine, which will be like our master. Okay, and we have to copy the public key and have to paste it and the authorized key of the second machine. So a passwordless connectivity can be established between these two machines. That's the last stage of this setup. Okay, come on. That's the last stage to this setup, and once that is done, okay, we'll be good to go to put our stuff. So thanks a lot for doing it out. Thanks a lot for like staying with me. It has been a long tutorial, but yeah, it will give you an idea how to build the multi-node clusters for executing the distributed deep learning workloads. Thank you so much.